Okay, we want to talk about two concepts here in probability, and the first one is conditional probability, and we'll give an example with rolling a die or tossing a die. So we'll say that we toss a single die, and so we have a sample space, which we'll denote with S, and it's this square, and ignore all these drawings in here for the time being. So when we toss a die, we can get a 1, a 2, a 3, a 4, or a 5. Just ignore the box here and the green here and the purple. So we have 6 different outcomes. That's our sample space. And then we're going to make up some events. So E will be the event of getting an even number, and so then E is equal to 2, 4, and 6. And then we'll make up another event, F. F will be the event of getting a number less than 4. So that would be 1, 2, and 3. So we'll denote those. The even number is E, so it's the green thing here because it contains 2, 4, and 6. And the blue box here is F. It contains 1, 2, and 3. So we have illustrated both the event E and the event F inside of the sample space S, and the reason it's inside is because events are always subsets of the sample space. Okay, now the next thing is we can ask, what's the probability of getting an even number? And everybody knows the answer to that. It's 1/2. But we can sort of do it more mechanically by using our formula for probability. So we want the probability of E, and the formula that we usually use is that the probability of something is the number of elements in it divided by the size of the sample space, or the number of elements in the sample space. And we said that this is E, so it's clear that the number of elements in here is 3. So we'll put a 3 in the numerator, and the size of the sample space, n of S, is 6. So we get 3 over 6, or 1/2, which is just what we thought. Now this formula that I said we should use is what we use for the classical probability situation. So that's when we're using classical probability concepts, not the relative frequency type of probability or probability concepts. Anyway, but just for illustration, I'm going to do it this way because it's the simplest way to do it. Okay, so that's just the simple probability of an event. Now we want to introduce this idea of what's called conditional probability, and the setup for that is here. So suppose I roll a die in my room, and I can see the result, but you can't see it. But I tell you that F has occurred. So I look at the die, and then I say, oh, F has occurred. And what does F mean? F was getting a number less than 4, so it means that one of these 3 numbers has occurred. And now I ask you again, what is the probability of E given that F has occurred? So I remember when I first was presented with this question, and I just thought, so what? It doesn't matter that F has occurred. Why should that change anything? The probability of E is the probability of E, so it's still going to be 1/2. So I initially wanted to say the answer to this question, that is, what is the probability of E given that F has occurred, given that we got something in here, I wanted to say that it's 1/2. But that actually is not the right answer. So why is it not the right answer? What's wrong with thinking about it like that, or how should we think about it? Okay, well, before we do that, let's just get some notation on the board. So the question I just asked was, what's the probability of E given that F has occurred? And I could sort of write it like that, right? The probability of E given F. So that I think is fairly easy to go from here to writing it like this and then writing it like this. But, in math, they usually don't want to write words like this, and they want to come up with some kind of symbol for this, or shorthand for this. And so they do. Instead of writing, they don't want to write this word, so instead of doing that, they put just a vertical line. So this would actually, you could write it like this, but generally speaking, you want to learn to write it the other way. The other way means putting a vertical line here. So that's what this is. So this is the probability of E, and then this vertical line is read given F, and we shouldn't be confused like I used to be. This has nothing to do with division. It is just a simple shorthand for this word given. That's all it is. So it has nothing to do with division. So how do we read this? The probability of E given F, not the probability of E divided by F. It has nothing to do with divided by. Okay, so we just converted this question in yellow here to here, these symbols. And by the way, this section or this slide is called conditional probability, and this question is called a conditional probability question. And why is that? Why would it be called a conditional probability question? Because this thing here that I've underlined is we're given that condition, we say. So given that this condition has occurred. So that's why it's called conditional probability, because we're given some condition and then asked what's the probability of E. So it's called a conditional probability problem. So this is a conditional probability problem, and the condition is here, F. So given F, what's the probability of E? Okay, so like I said, I would initially have wanted to say, well, so I don't care if we're given that F has occurred. So what? I just want to say the probability of E is 1/2, and I don't care what we were given. But it's going to turn out that the answer is actually 1/3. Now, why is it 1/3? Well, remember, in this question, we're given that F has occurred. So is it possible that we got a 4? No, that's not possible, because we know that F has occurred, and F is here, this square box, this blue square box here, or a rectangle here. So 4 is not possible if we know that F has occurred. And the same thing with 5, and the same thing with 6. These are just not possible. So basically, the only things that are possible are the things in F, because we were given that F has occurred. So we can sort of say that this is the new sample space. This is the new set of possibilities. The whole sample space, original sample space S, is no longer the set of possibilities, because these are not possible. So this is the new sample space. So we can think of it that way, first of all. And so then that means that in our calculation here, when we're answering this question, the sample space should be F. So not S. So we shouldn't take n of S. We should take n of F. So we're going to have n of F in the denominator, not n of S. Okay, not n of S. Okay? So, and then next, well, before we said it would be n of E, but not all of E is actually possible anymore, for the same reason. We said that only things in F are possible. So, is it possible to get a 4? Is it possible to get a 4? No. We said that F has occurred, so 4 is out of the question. And how about 6? Is that possible? No. The only way to get an even number now, given that F has occurred, is if we get a 2. So in general, more generally, the only things that can, if we want the probability of E given F, the only things that we can look at are the things in E that are in F. So that is, we have to think about just the intersection of E and F, not all of E. So we want to know how many things are in there. So we want to say we want n of E intersect F on the top, not just n of E, not all of E, but only the part of E that intersects with F. So this is actually what we want to figure out what this is, and this is easy to figure out. N of F is 3, and E intersect F is just this element here, so there's only 1. So that's 1 over 3. And so that is the answer to the probability of E given F. That is, what is the probability of E given that F has occurred? It's 1/3. And this is how we got that answer. Now, usually, they don't usually write it with N because it's usually in, we're talking in the setting of probabilities, and we could leave it like this, but anyway, by the way, this formula, as I said, only really works when we're talking about classical probability, but the idea is correct, and so I'm just going to leave it like this because this is the easiest way to understand it. But usually the way it's written is like this. Whoops. Usually the way it's written is like this. The probability of E given F, the probability of E given F is not N of E intersect F divided by N of F, but it's P, probability of E intersect F, divided by the probability of F. So how can we get from here, from this expression, when we saw where this would come from, we showed it over here in the picture, how can we get from here to here? Well, I can just divide, if I divide the top by N of S and the bottom by N of S, then I'm not changing anything. So let me do that. I'll divide this by N of S, and I'll also divide this by N of S. So how does that help? How does that help get me from this divided by this to this divided by this? Well, what is this? P of F. Well, using this idea here, what is it? What is P of F going to be? If P of E is N of E over N of S, then P of F is N of F over N of S. But what do I see here? N of F over N of S. So this is exactly this. Okay, so we got that piece. Now, where did this come from? Well, what is the probability of E intersect F? Well, it's the same idea. If the probability of E is equal to N of E over N of S, so the probability of this thing is what? N of this thing divided by N of S. So what do you see here? You see N of that thing divided by N of S. So what is that? That's this. So I showed that this thing is this, and this thing is this, and so I've shown that the probability of E given F, which was equal to N of this divided by N of this, but then we divided both sides by N of S, or both the top and the bottom by N of S, and then we saw that this part can be written like this, and this part can be written like this. So we can rewrite this thing as this, and this thing was meant to, we showed that this thing was the probability of E given F. So now we have the probability of E given F is P of this thing divided by P of F. And so that's how we explain what we mean by the probability of E given F. Now, we know what we mean by it because we explained it in English, but actually this is actually the real definition. So it's not, anyway, it doesn't matter. This is the formula for the probability of E given F, but usually we say it's not just the formula, it's the definition. Okay, so to see some of this in our textbook, let's go here. So we talk about here conditional probability, and here's the notation, which is what we used, and this is how to read it. The probability of A given B, the probability of A given B. And they give some example here. So this is not an example with dice, so let's go through this example. It's another example. So this is some kind of table, and we can see that it's divided into men and women, and whether they were promoted or not promoted. And this is the promotion status of police officers over the past 2 years. So here this number 288 is in the men's column, and it's in the promoted row. So what does it mean? It means 288 police officers who were men and were promoted. And here this is 36 police officers who were women and who were promoted. And this is 672 police officers that were men and not promoted, and 204 police officers that were women and that were not promoted. So this is some data. And if we want to think about this as a sample space, we would kind of turn it into a question like that by saying, suppose we selected a person at random from this group. So that would be like, suppose we rolled a die. And then we would say, what are the chances that we got a man? Or what are the chances that we got a woman when we selected one person at random from this entire group? Or we could say, what are the chances that we got someone who was promoted? Or what are the chances that we got someone that was not promoted? So that's the idea. That's how we can turn this table into the language of probability that we're sort of used to using. So the sample space is all the people. We choose one person at random, and then whatever these columns and rows mean, this is like an event. The event that we get a man, the event that we get a woman. So we have all of the people, and then the men is just a subset. And remember, all of the people is the sample space, and men is just a subset. So, but a subset of the sample space is an event. So if we could talk about the event of drawing a man from the group, or another subset is the women, we could talk about the event of getting a woman from the group. And the same thing with promoted. Promoted could be an event, because that's also a subset. That's these people. And not promoted is also another subset. That's these people. So we have the event of drawing a person from the group who was promoted, and also the event of drawing a person from the group who was not promoted. So we can see this table in light of our previous discussion of sample spaces and events. And we can ask how many men are there in this group, and that you just take this number plus this number, and you get this. So apparently there's 960 men in the group. And how many women are there in the group? There's apparently you add this and this, and you get 240 apparently. So there are that many women. And how many people are there in the group altogether? Well, somewhere in here it probably tells us that there are 1,200, but we can also get that just by saying, well, we have 960 men and 240 women. So the total number of people is, when you add these up, is 1,200. Or you could say I got 324 promoted and 876 not promoted, so the total is, again, 1,200. Okay, so probably in this discussion they're going to talk about one event given another, and we've just identified 4 different events: men, women, promoted, not promoted. So probably in this discussion they're going to ask something like, given that it's a man, what's the probability that they're promoted? Or given that they're a man, what's the probability that they're not promoted? So probability of one event given some other event. We've identified 4 different events here. They're probably going to ask some question like that. So they're going to put this into a question about discrimination. So they're going to ask, were the women discriminated against? In other words, were they unfairly not promoted as much as the men? So that's the kind of general question we're trying to ask, but we have to put that question, we want to try and put that question into a conditional probability question. That's going to help us to answer the question of whether there was discrimination. So let's see how they bring this up in terms of discrimination. Let's see what they say. So they say, after reviewing the promotion record, a committee of female officers raised a discrimination case on the basis that 288 male officers had received promotions. 288 males had received promotion, but only 36 females had received promotions. So right there you might think, oh, maybe there's some kind of discrimination, but that's not quite, that's not quite good logic. And let's see why not. The police administration argued that the relatively low number of promotions for female officers was not due to discrimination, but to the fact that, there aren't very many women compared to the number of men. So we would expect fewer women would be promoted just because there are fewer women in general. So it was not due to discrimination, but to the fact that relatively few females are members of the police force. Let us show how conditional probability could be used to analyze the discrimination charge. So here they're going to define these events. M is the event of selecting a male. W is the event of selecting a female. A is the event of promoted, and A complement, or not A, is the event of not promoted. So we have M, W, A, and A complement. Okay, before we attack the conditional probability question, let's think about what would this mean? M intersect A. So what does that mean? That's man intersect promoted. But remember, we've said that intersection can be read as the word and, A-N-D. So we could read this as M intersect A, but we could also read it as M and A. So that means male and promoted. So how many males are there that were promoted? Well, here are the men, and here are the ones that are promoted. So the intersection has 288 police officers in it, and the probability of that would be 288 out of the total 1,200. So the probability of M intersect A is 288 out of 1,200. Okay, so that's just a separate problem. It's not a conditional probability problem yet. We're just doing this problem, and the number turns out to be this, 0.24. And then we could also ask another question. This is still not a conditional probability question, but this is what? This is asking a question about M intersect A complement. So that means what? It means a man who is not promoted, or a male and not promoted. Male intersect not promoted. So where are they? These are the men that were not promoted, 672. So the probability of that is 672 out of 1,200. And then we have women and promoted and women and not promoted. And we get these numbers here. These kinds of questions here where you do intersections, they are called joint probabilities when you do these intersections. When you have a table like this, and you do like promoted so remember that promoted is an event. It's a subset of the whole sample space, and it's an event. And man is also an event. So man is this event. So the intersection is also an event, and it's called the joint. So this intersection is called the joint probability of promoted and men. Sometimes it's called that. So they say because each of these values gives the probability of the intersection of two events, the probabilities are called joint probabilities. So each of these is referred to as a joint probability, which provides a summary of the probability information for the police officer promotion situation. And this is referred to as a joint probability table. That is here, this table here. So the 0.24 is here because it's men intersect promoted, and the chance of that is 0.24. This is 0.56 because it's men not promoted, and men not promoted was 0.56, and so on. We can fill in all of these. And then these here and these here are called marginal probabilities. So these are the joint probabilities, and then what's here and these two here are called marginal probabilities, and that's because they're kind of in the margins here. Right? This is in the margin, this is in the margin. So they're called marginal probability. And what do they tell you? They tell me this one tells me the probability that we got a man. And where does that come from? It's the sum of men and promoted probability and men and not promoted probability. That's all the men. And that turns out to be 0.8. And you could have also gotten that just from looking at here. 960 divided by 1200 would give you the same thing, would still give you 0.8. But we can do it from here as well. So we can say the probability of men is 0.8, the probability of women is 0.2, and they wrote that here. Probability of men is 0.8, probability of women is 0.2 here. Probability of A is 0.27, promoted, and not A or not promoted is 0.73. So those are given here as well, and they're called the marginal probability. And if you want to know the probability of being promoted, it's the probability of being a man and being promoted plus the probability of a woman and being promoted. That's this plus this, which is this. So that's the probability of A. So the probability of A is the probability of man intersect A plus the probability of woman intersect A. We get 0.27. And that's a marginal probability. Okay, so finally, after all of that, we're going to get to conditional probability. So they're going to calculate the probability of A given M. And why are they doing that, by the way? Because they want to know, well, this is going to give us what? Given that it's a man, what's the probability of being promoted? And then later on, they're also going to want to know the probability of A given W. So A given M and A given W. So A given M is given that it's a man, what's the probability of being promoted? And this is given that it's a woman, what's the probability of being promoted? And let's see what the answers are before we think about how to get these answers. So the answer for this one is 0.15, 15%. So if you're a woman, the chances of being promoted is 0.15, 15%. And what was it for the men? 30%. This was men given, given that you're a male, what's the probability of being promoted? So I think that does answer the question about whether there's discrimination happening. Now, it doesn't mean that there's unjustified discrimination, but there is a difference between the way men get promoted and women. Now, there could be like a legitimate reason for that, or there may not be a legitimate reason for that, but it's definitely happening. From the data, we can see that it's happening. So, because this is 30% chance of being promoted given that you're male, and only 15% chance of being promoted if you're a woman. So what conclusion do you draw? The probability of a promotion given that the officer is a man is 30%, twice the 15% for a woman. Although the use of conditional probability does not in itself prove that discrimination exists in this case, the conditional probability value supports the argument presented by the female officers. Okay, now how do we do these calculations? Well, we already learned. They're explaining how to do probability, but we already discussed it, and we already gave the formula for the probability of A given B. We said that it's the probability of the intersection divided by the probability of B. Remember, we said this here. The probability of E given F is E intersect F over F, or the probability of E intersect F over the probability of F, or they're doing A given B, so it's going to be A intersect B divided by the probability of B. The probability of A given B is the probability of A intersect B over the probability of B. So we already discussed this, where it comes from. So we can just figure these things out. We can say, what's the probability of A given M? We just take the probability of A intersect F. Remember, A intersect M, remember we called that the joint probability of A and M. So we actually calculated that, and it was 2.24 somewhere along here. 0.24, there it was. And then we divide by the probability of M. Remember, we called that a marginal probability. Where was that? That was the probability of men was here, was 0.8. So I hope we divide by 0.8 there. Yeah, 0.24 divided by 0.8. So we can figure out, given that it's a man, what's the probability that they get promoted, and it was 0.3, and then we can do the same thing for a woman, and it gets 0.15. So we have used conditional probability to investigate this question of discrimination between the sexes. Okay, so now we need to cover one more topic, and that's called independent events. Okay, so let's just take a snapshot of this so that we can refer to it in the next section. This was what we just discussed, conditional probability. This was the definition. I gave it to you as E given F, but here we're doing A and B. It's the same thing. Let me just take a snapshot of that, and let me put it in my screen. So just so that I have it, this is the definition of the probability of A given B, and we talked about it extensively already. It's the probability of the intersection divided by the probability of B. Okay, now we want to introduce one last topic, and that's called independent events. Now, let's just, here they're going to give us the definition. They're going to explain it, but let's just look at it, what they say, because I just want to compare it with the other formula that we just looked at and see that it's there's something different here. So, first of all, what are they? Here's the definition of independent. So they say two events A and B are independent if this. Now, it doesn't. We haven't discussed this concept yet, so we don't know why they're making this definition. I just want to point out that this is different, and let's see how it's different from what we just saw. So I'll take a snapshot of this and put it on the same board as what we had before. Okay, so let's just see what's. I mean, there's some difference here. We're talking about something different, and hopefully there's some difference. Okay, but here on the left side we have. This is the definition of this symbol. That is, the probability of A given B is actually defined by this. Okay, now, what about this? Is this the same as this? Well, on the left-hand side, they're the same. But on the right-hand side, they're obviously not the same. So, two events are independent if this is true, but this is just the general definition of this symbol. So this isn't always true. Two events are not always independent. They're independent if this is true, but this isn't always true. Two events are not always independent. But this is always true because this is just the definition of this symbol. It's not under special conditions this equals this. This is the definition of this. But this is only true if the events are independent. Otherwise, this is not true. So let's read this and see what it says. What does it say? It says the probability of A given B is equal to the probability of A. So what does that mean? What do you think this means? It means that even if we're given B, the probability of A given B doesn't matter that we were given B. The probability of A given B is just the probability of A. So actually that goes back to our earlier discussion where I said the probability of even given, remember at the very beginning of this discussion I said, I asked the question, what's the probability that it's even given that the number is less than 4? And I said, originally when I saw that question, I would have said, oh, it doesn't matter that I'm given that the number was less than 4. Why should that matter? I'm just, the probability of even is 1/2, period. That's what I wanted to say when I was younger. But I guess I was wrong. But what I was thinking, I guess, is that given F doesn't make any difference, or given B doesn't make any difference. The probability of even given something doesn't matter. It's just the probability of E. So what I'm saying is it didn't matter that I was given F. That is, I was given that the number was less than 4. I don't care. In other words, what I was actually saying in this language is I'm saying that even was independent of being less than 4. That's what somehow I was saying, but that's not true. But but that's what we mean by saying that two things are independent. If you're given B, it doesn't matter whether you're given B or not. The probability of A given B is the same thing as just the probability of A. That's the concept of independent events. If that's true, if given B doesn't affect calculating the probability of A, we say that A and B are independent of each other, but that's not always true. In fact, actually, it's rarely true. So that is the idea of this, and I just wanted to show you that this formula is not the same as the conditional probability formula. Right? They're not the same, right? So let's read the lead up to this definition here. Let's read this paragraph. So in the preceding example, the probability of A was 0.27. The probability that was what? Promotion was 0.27. Given that you're a man, promotion was 0.30. Given that you're a woman, the promotion was 0.15. So we did all of this stuff, I guess, before. We see that the probability of promotion, that's A, is affected or influenced by whether the officer is a man or a woman. Because if you're a man, it's one thing, and if you're a woman, it's another thing. And if we don't know whether it's a man or a woman, then it's in yet another number. So this is not the same as this is not the same as this. And then they say, particularly because the probability of A given M is not the same as the probability of A. So that's this, right? The probability of A given M is equal to the probability of A or not. But here, it's not. The probability of A given M, so that's this one, 0.3, given that you're male, the probability of being promoted is not equal to the probability of promotion. That means that being promoted and being a male are not independent. In other words, if you're a male, that changes what the probability of A is, because the probability of A just by itself, according to this, and we did this somewhere before, the probability of A is 0.27, and then given that you're M, that changes things. So the probability of A given M is not equal to the probability of A. If it was, then we would say A and M are independent. We would say that being promoted is independent of whether you're a male or not. But it's not that case, because this is 0.27, but it jumps up to 0.30 if you're a male. So being a male affects whether you're going to be promoted. So male and promotion are not independent. And that's where this definition comes from. So it seems natural to say that this would be a definition for independence, because it's A and B are independent if given B doesn't affect the probability of A. It's the same as just the plain probability of A. Or in this case, given that you're male, it doesn't affect whether you'll be promoted or not. But it does in this case. So they're not independent. So let's read on. We see that the probability of a promotion, event A, is affected or influenced by whether the officer is a man or a woman. Particularly because the probability of A given M is not equal to the probability of A, we would say that the events A and M are dependent. They're not independent. That is, the probability of event A, promotion, is altered or affected by knowing that event M, the officer is a man, exists. Similarly, the probability of A given woman is not equal to the probability of A. We would say that events A and W are also dependent, not independent events. However, if the probability of A is not changed by the existence of event M, that is, the probability of A given M equals the probability of A, here, A given B equals the probability of A, we would say that A and M are independent. This situation leads to the following definition of independent events. So now we have kind of a justification for why we would make this definition for the word independent events, or the phrase independent events. And it could be A given B equals probability of A, or it could be B given A equals probability of B. So it's the same statement, really. Okay, let's go to the next topic in this section. So this is called the multiplication law. And this just is, remember the definition of PA given B was just putting this part underneath here. So this is nothing but bringing the denominator over to here. So in other words, it's just taking this part and bringing it up here. So we get the probability of A intersect B equals something over here which has two terms, has this term and this term. So there it is. The probability of A intersect B is these two terms. So that's nothing really but a rewriting of the definition of this, or rewriting that equation. And if you rewrite the definition of this one, because this would be over here before, and you just bring it up here, you get this. So you can write PA intersect B as the probability of A given B times the probability of B, or you can write it as the probability of B given A times the probability of A. So they call this the multiplication law, because you can see that it gives you an expression for the intersection in terms of a product, right? We have a product of these two things, or we can have the product of these two things. So this is called the multiplication law. So, what it does is it gives us an expression for the probability of A intersect B. Actually, we have two ways of writing it, but really they're the same thing. So, but in some sense they're different. But anyway, this is the probability of A intersect B. And we can get it as the product of this and this, or this and this. Now, like I said before, this is always true. This is really, I called it the definition of this is this, so it's always true. But this is not always true. When this is true, we call A and B independent, and it's not always true that A and B are independent. So this is not always true. But if it is true, what happens to that multiplication rule? So if this is true, what happens to the multiplication rule? So the multiplication rule, let's take this form, has A given B in it, probability of A given B. But we're saying that if they're independent, then we can say probability of A given B is just the probability of A. So if they're independent, we can write this, what? As just the probability of A. So then we get a very simple, kind of easy to remember rule for intersection, probability of intersection. The probability of intersection, if A and B are independent, we get something very simple. It's just the probability of B times the probability of A, not A given B. So that's what we write next. If they're independent only, then we get a very simple expression for the probability of A intersect B. It's just the probability of A times the probability of B. But that's not always true. What is always true is up above. This is always true. The probability of A intersect B is this times that, but when they're independent, this just becomes the probability of A. So we just get the probability of A times the probability of B, and that's if they're independent, and that's this. So let's copy that and put that on the board. So there it is, a very nice rule, but it's only true when A and B are independent. Now we had another very nice rule before, maybe a couple lectures ago. If I go back to an earlier section, we had something called the addition law. Now, let's take a look at that. So this was the addition law, but this one was not so simple. Just like the multiplication rule that we have now was not so simple, but under certain conditions it did become simple. Under certain conditions, it became this. It wasn't like that. I don't want to go back and bring it up again, but this term was more complicated. But now it's very simple, but that's only under a special case. The same thing here, actually, and we did this already. This is the addition law. It's not so simple, but under a special condition, which was what? If the two events not independent, the one we just finished was if they were independent, but this became simple if the two events were mutually exclusive. So let's scroll down and find that. When they're mutually exclusive, then it becomes very simple. Let's take a copy of that and put it up on the board too. So now we have this also. So this, under a special case, is true. When the two events are independent, we can say intersection becomes multiplication. And when the two events are mutually exclusive, union becomes plus. But these are, when they're independent, when they're mutually exclusive, when they're independent. Then we get these simple expressions, but we don't get the quite as simple if we don't have that condition or this condition. Okay, so we have covered these two topics together. They're quite important, and we've covered them in good detail. We've covered conditional probability and independence. And you should go back and review the chapter again, or rather these sections again, and make sure that this is clear. Independence and conditional probability.